Thanks for joining us tonight. It's the second Tuesday of the month at UW Space Place, so we have a guest speaker as always. And tonight I'm very pleased to introduce an astronomer who's been closely associated with UW Space Place for quite a while. Catherine Witherspoon has been a loyal volunteer here at Space Place for many of our programs for years, helping us do outreach. But at the same time, she's also been a graduate student working on her PhD in astronomy here, and specifically working on how galaxies work. So tonight, Catherine is going to tell us about turning out the lights in galaxies. So I hope you'll join me in welcoming Catherine tonight.
Hello, everyone. Can you hear me in the back? Great. Okay. So, as you said, I'm a sixth-year grad student working with Eric Wilcox, also known as Dean of LNS. I was supposed to say that. So, some of the questions I want you to think about tonight while I'm giving this talk are just, how do galaxies evolve? What can you think about when you hear the phrase, how do galaxies evolve? And then also, how can we stop forming stars in galaxies? So I'll just give a brief outline of what I'm going to talk about tonight. So I'll give a brief background of how do stars form, because if you want to know about how stars stop forming, you need to know how they form. So then I'll talk about how you might shut down star formation. What's an AGN? We'll get to that. And then why should my research focus on low-mass galaxies smaller than our own Milky Way? And then I'll get into my current research. So with that, let's get started. So when I look at all these different types of galaxies, I see red galaxies, I see blue galaxies, I see some with spiral arms, I see some that are just a blob with a nice bright nucleus and a halo surrounding it. Some have weird features, others are just uniform. So why do all of these galaxies look so different? And Edwin Hubble looked at these galaxies and said, oh, maybe we can sort these in some way. So let's separate them into elliptical galaxies on the left and spiral galaxies on the right. And we're going to further split those spiral galaxies into ones that just have a nucleus and spiral arms radiating out from that nucleus, and then barred spirals, ones that have, it looks like a bar in the center with the spiral arms coming out of that. And he said, okay, well, I think we can relate the morphology of a galaxy to its evolutionary track. And we think that elliptical galaxies they're on the left, they'll evolve into a spiral galaxy on the right in some way. Now, this actually ended up being the reverse of what we think is true today. We think that spiral galaxies are forming stars, and then something happens to merge them into an elliptical galaxy. And I'll get into that a little bit more later. But we now have this idea of elliptical galaxies, spiral galaxies. Their morphology can relate to their evolution over time. But I asked this question already, why do these galaxies actually look so different? And the reason is because they're made up of billions of stars. So you're not looking at one object, you're looking at billions of objects all interacting with each other and merging together. So the light that we see from all these objects is combined. So if we want to talk about a galaxy, then we need to talk about an individual star and then talk about a bunch of stars. So a star is any object that fuses hydrogen into helium and releases energy. So our sun is a star. And if you think about a fire, the same is true here. The temperature corresponds to the color. So a blue star will be really, really, really hot, much hotter than a fire, of course. And a red star will be really, really cool. Now, on this diagram, I'm just plotting how bright the object is on the y-axis, and on the x-axis, how hot it is. And so you see that these blue objects, these blue, really hot stars, are also going to be really, really bright. And your red objects are generally going to be really, really cool and dim. So if these hot, bright stars actually run through their hydrogen fuel faster than the cool, dim stars, this can tell us a little bit about the life cycle of a galaxy. So if we see a blue star that's really, really bright, then it probably formed really, really recently, okay? So that gives us an estimate of the star formation rate of these galaxies. I see this star, it should have gone supernova by now, but it hasn't. So that means it's really, really young. So that brings us to the galaxies. We know that the color of one star can relate to the temperature, and it can also relate to the lifetime or the age of that star. So then if we look at billions of stars all combined, we see that the color of the galaxy overall can relate to, one, morphology, I already said that, but two, it can relate to the star formation rate. And if most galaxies are on this main sequence, they're forming stars steadily, they're probably going to be blue. But if they're passive, not forming very many stars, they're probably going to be red. So that's where that term that you might have heard, red and dead galaxies, that's where this comes from. Okay. But I went through this all assuming that you knew what a star was. So now let's say, how do stars form? So what you need for a star is you need gas, and you need it to be cold and dense. So it's going to start out with some cloud of gas in space. For whatever reason, that cloud is going to become clumpy. It's going to condense a little bit. And then even denser cores are going to form in these smaller clumps. And then finally, it'll get dense and dense and dense enough to heat up that interior and produce a protostar. And over time, that protostar will evacuate its surroundings. The star will form. You might get a few planets. And then maybe that star was big enough to go supernova in the end. And then you'll have this cloud of gas again, and the cycle will start all over again. So I've now said you need stars to form, but what do you need to shut down star formation? So if you need cold, dense gas to form a star, then you need to change the properties of that gas in some way so it's not cold or dense, or you need no gas at all. So here are some of the main mechanisms that we think of when we want to shut down star formation. So one, the galaxy simply runs out of gas. No gas, no stars. And this could be as simple as the galaxy had gas, it formed a bunch of stars, now there's no more gas. It's not going to form any more stars. Another mechanism is the start of really bad naming in astronomy. It's called gas stripping, and this is where the galaxy is moving really, really fast through space, and some of that gas will get stripped, fall out behind the galaxy. So it looks kind of like a jellyfish in that way. And if you've taken out that gas, then there won't be any more gas, so the galaxy will stop forming stars. The next mechanism is called starvation or strangulation. Fun titles. This is, instead of removing the gas, you stop gas from coming into the galaxy. So it's the same as mechanism one. Once you use up all the gas that's in that galaxy already, you have no more fuel for star formation, and the galaxy becomes passive. It shuts down. Next, we have stellar feedback. So this is really massive stars. They can produce winds, kind of like you think of them here on Earth. They push stuff away from them, and this can push gas out of the galaxy, kind of in this bottom right picture in the red. you see the gas flowing out of the galaxy. Or you could have a supernova, and that could heat the surrounding gas and push it out. So either the gas has been heated, so it's not cold enough to condense, or it's just no longer in the galaxy. And finally, we have feedback from massive black holes, and this will do the exact same thing as stellar feedback, just from a different source. It'll either heat its surroundings, or it'll eject that gas out of the galaxy. And I'm going to split these mechanisms into two separate ideas. We have the environmental or external to the galaxy mechanisms. Something is acting upon the galaxy. And then we have internal mechanisms, ones that are intrinsic to this galaxy. There's stars in the galaxy that are exploding. There's a massive black hole in the galaxy that's heating its surroundings. So how can we distinguish between what's actually shutting down the star formation in these galaxies? You need to look at them one at a time and try and split between, or distinguish between whether these are environmental effects or something internal to the galaxy. Okay, so I mentioned these massive black holes, and I'm going to rephrase that a little bit. So I phrase this as, what are active galactic nuclei, or AGN? These are just black holes that are really, really, really massive at the centers of galaxies. And the interesting thing about them is that they're not just sitting passively in the center of the galaxy. They're actually eating up their surroundings. They're actively accreting whatever's surrounding them. And so the way you might think of this is that you have the black hole in the center, you have this accretion disk of material that's slowly circling around the black hole, getting closer and closer and closer to the black hole before being sucked up. You might have a jet of material that's pushed away from the black hole because too much is falling onto the black hole. It just can't keep up with how much is being put onto it. Or you might have this dusty orange, in this case orange, dusty torus. It's a donut shape of material surrounding it. And this actually is really interesting because this dusty torus could get heated, and then you can see like infrared light from this dusty torus, and that might tell you that there's an AGN there if you see infrared emission from a galaxy. And then you might also have these surrounding gas clouds. And these gas clouds are really important because they offer a completely separate way of identifying an AGN. There's a lot of energy coming from this black hole, and it can heat up these gas clouds. And so you might get emission from these gas clouds like oxygen, hydrogen, nitrogen. And if you see really hot oxygen, that can say, oh, well, a star can't do that, so it must be something else. And in this case, it's probably a black hole. So then finally, why do I want to focus on low-mass galaxies? So in my first year here, I was supposed to look at the colors, red, blue, anything like that, of galaxies in a survey. And the point was that there are galaxies all around us, and we saw that the colors of these galaxies changed over time. Great. But they also changed over time as a function of how massive they were. So I'm looking at the stellar mass on the y-axis here as a function of the redshift, or how far back in time we're looking. And we see that these really high mass galaxies up here are very red, and they stay red no matter how far back we looked in time for this survey, which means that they're not changing much. They're not evolving as much as these low mass galaxies, which were very clearly changing from very blue to starting to get red. And the point we wanted to make there was that these low mass galaxies were the perfect environment for looking at the evolution of galaxies right now, at this point in the universe. So these low-mass galaxies are just in the process of shutting down their star formation, which I'm using as my mechanism to say that these galaxies are evolving. And the other interesting thing about low-mass galaxies, other than that they're shutting down star formation now, is that we've only just started to find AGN in these galaxies in the last decade. It used to be that AGN were thought to be only in these much higher mass galaxies. And there were a couple serendipitous discoveries in the last decade that said, okay, so we might not have been right about that. Are there other AGN in low-mass galaxies that we just haven't seen? And the answer is yes. So now we have this entirely new mechanism of shutting down star formation in low-mass galaxies that has not been explored before. So that's where my research comes in. So I look at how low-mass galaxies stop forming stars. I look at what effect an AGN might have on a low-mass galaxy. Is it going to heat the surrounding gas? Is it going to blow it out? Who knows? Let's find out. But in order to do this, we needed to first distinguish between those external and internal effects on the galaxy. So I'm going to distinguish between the effects of the AGN inside the galaxy and the galaxy's surrounding environment. So in this case, I'm going to say that the environment is how many galaxies are nearby. Can we look at that kind of neighborhood of the galaxy? So let's get into where my sample comes from. So I look at the MaNGA survey. This is the Mapping Nearby Galaxies at Apache Point Observatory survey. Quite the long name. But the point is that it was a survey of almost 10,000 nearby galaxies, nearby being relative. It's hundreds of thousands of light years away. And they use the integral field unit spectroscopy, which is looking at a galaxy and splitting it up into a bunch of different parts. They're called fibers. And at each individual point in the galaxy, they're going to take a spectrum. And by that, I mean they're going to say, let's split up all the light we receive from that one point, and we're going to say, yes, that's green light, that's red light, that's blue light. And then they're going to do that across every single point in that galaxy and get a map. So one, you'll get the entire galaxy in green light. In one, you'll get the entire galaxy in red light. And it's really useful. So here's one of the galaxies that I have been looking at. It's kind of small because it's low mass, so there's not much to it. And it's going to get a spectrum of every single point in this pink hexagon. So on the left here, I have the gas velocity within that galaxy. So it's rotating. It's not rotating very nicely, but it is rotating. It's different from the stellar velocity that we've been looking at, which is much more ordered. Nice line in the center here. And then we can also get distributions of the gas. So in this case, I'm looking at hydrogen, and that tells me that there's this nice offset point of hydrogen here. It's not located directly in the center. And then I can get a spectrum at, in this case, it's the very center of the galaxy. And that tells me that there's a lot of nitrogen and a lot of oxygen. So as I said before, a lot of oxygen typically means that there's going to be an AGN or something heating that gas. And in this case, it's an AGN. Okay. So that's how we've looked at our galaxies. And from the MaNGA survey, out of those 10,000 galaxies, about 3,000 of them are low enough mass to say, yes, I want to use this in my sample. And the other part of my survey is I said, well, I want to know how the star formation is changing in these galaxies. Are they forming a lot of stars, or are they forming a couple? And so I'm going to call those galaxies with very little star formation quenched, just like you're quenching your thirst, anything like that. So in order to say that they are star forming or quenched, I'm going to plot their star formation rate, and I'm going to plot their mass, and then I'm going to say, okay, anything that's star forming will be well up on this diagram, and anything that falls about an order of 10 below most of the galaxies on that plot will be considered quenched. And so this gives me about 450 quenched low-mass galaxies. And then I need to select my AGN. So I've said before that we want to see a lot of oxygen, a lot of nitrogen, because only AGN can produce the energy required to heat that gas to these significant levels and produce this type of gas. So I'm going to plot how much oxygen I see and how much nitrogen I see for all of my galaxies. And if anything falls below this blue dashed line, I'm going to say, okay, no, that's not an AGN. That's purely driven by stars. So that's going to be part of my non-AGN sample. But if it falls above this red line, we can be fairly certain that something massive is heating that gas. And so I did this for every single galaxy and found 41 low-mass AGN out of 3,000. That's not bad. Pretty low statistics, but considering that we've only started finding AGN within the last decade, it's not bad. And about 11 of my AGN are quenched. They have low enough star formation rates that I say, there's not much going on here. Okay, so now that I have my samples, let's look at the environments of these galaxies, because if we want to know what the AGN is doing, we have to distinguish it from the environmental effects. So, as I said, the environments of these galaxies are like their neighborhood. We're going to look within a certain radius of each target galaxy, and we're going to count the number of galaxies that fall within that radius. Anything else is probably going to be too far away to really make a difference on our target galaxy. So, looking purely at all of the galaxies in MaNGA, not just the low-mass galaxies, I'm splitting up the number of galaxies that we see in each panel by their mass, so low mass on the left end and high mass on the right. And then I'm going to look at the size of their environment, so how many galaxies are nearby. And in blue, I'm showing the samples that have a fair amount of star formation. And in red, I'm showing the quenched sample. There's not a lot of recent star formation happening. And so we see here that the low-mass galaxies, one, there's a lot more star-forming low-mass galaxies than quenched low-mass galaxies, as opposed to the high-mass galaxies, which goes back to that plot I showed a bit earlier, where I said the high-mass galaxies are already red and dead, while the low-mass ones are just beginning to shut down their star formation now. And we see that here. Most of the high-mass galaxies are quenched, or at least a good fraction of them. The other thing to notice is that the low-mass galaxies, and a little bit too the intermediate-mass galaxies, tend to be in low-density environments. There aren't a lot of galaxies nearby them. And in fact, a good fraction of the low-mass galaxies are isolated from any other galaxy. So if anything's happening in those galaxies to quench them, then it's going to be internal. There won't be environmental effects. Another way to look at this is, instead of looking at the number of galaxies that we see in each of these bins, this is the exact same plot, just a cumulative distribution function. And what that means is that we're looking at the probability that our galaxy falls within a certain size of environment or lower. So about 80% of our low-mass galaxies are isolated, while let's say like within a size of 15 galaxies, that adds another 10% of our sample. While for the quenched sample, we're only looking at about 60% of our galaxies are going to be isolated. And then there's a much longer tail of these galaxies that become quenched due to their environment as we go to larger and larger environments. Okay. So now that I've talked about the environments of all MaNGA galaxies, let's look at just the low-mass galaxies and compare the AGN to the non-AGN. So I have my total sample on the left here, my quenched samples in the middle, and then star-forming samples on the right. And the difference in color here is that the blue ones are the non-AGN, and the red ones are the AGN. So I've switched things up a little bit. But I still have my cumulative distribution function, and so if we look in the middle panel, we see that the quenched AGN, almost all of them are isolated, or if not isolated, have very few nearby galaxies compared with the quenched non-AGN. And this red line, or this blue line here, is the same red line that we saw here. So these AGN-1 are more likely to be found in low-mass groups, but there's also no statistical difference between the samples of star formation. So the AGN and the non-AGN that have a fair amount of star formation, their environments look fairly similar, and we can't say anything about them. The quenched sample show a marked preference for isolation or these low-density, low-mass groups. So, a quick summary of what I've just talked about. Of the low-mass AGN in my sample, 53% were isolated, 16% were isolated and quenched, and if we just look at the quenched AGN, 60% of them are isolated, which means that whatever quenched those galaxies was probably not environmental, unless another galaxy crashed into that galaxy and we're just seeing well down the road in evolution. So maybe something did happen, but we don't know. So we can only say that there's a bit of a correlation between the isolation and the quenching of these AGN. Okay, so moving on. Now I want to focus more on the interior of these galaxies with AGN. So I'm going to study the gas distribution and kinematics of these low-mass AGN. So I'm going to go back a little bit and say, how did we observe this gas? Okay, so I took it from MaNGA, but how did they do that? They used spectroscopy, as I said, emission and absorption lines to look at how much gas was in each region of the galaxies and how fast it was moving in each part of the galaxy. But that only told me about gas that we can see in the optical with our own eyes, if we could stare long enough for hours without blinking. The gas I'm actually going to talk about is called H1 21 centimeter emission. H1 is just hydrogen. It's not very hot, it's actually pretty cool. And the point of it is that in a hydrogen atom, you have one proton and one electron, and there's more energy in the system when the proton and the electron are aligned. And as soon as that electron flips, there's less energy in the system. And that releases a very well-known amount of energy. And the wavelength of that light that you see is 21 centimeters. So if we look anywhere in our galaxy, you're going to see this 21 centimeter emission. It actually traces spiral arms of galaxies really well. And if you know about looking at rotation curves of galaxies. We've used 21 centimeter emission to extend further out into the galaxy from the known stars. And it tells you how fast our galaxy is rotating at certain points. So I'm going to produce that kind of plot that you see here for 10 of my low-mass galaxies with AGN. So I use the Very Large Array, the VLA, in New Mexico. It's a radio interferometer, so it's a bunch of radio telescopes set up in an array, kind of like a Y here. And I'm going to produce these resolved maps of H1 gas, distribution, and kinematics. So here is one of my detections. As you can see, I'm stepping through velocity space. So this galaxy has rotation. And I see a little bit of gas here, and then as we're looking at different velocity gas, it moves across the galaxy. That's how we know that there's rotation. And that's great and all, but that wasn't the galaxy I was observing. That was the companion that was right nearby. It was that nice blue galaxy, while my AGN galaxy is this elliptical blob over here. And what that tells me is that there's not very much gas in my AGN galaxy. All of the gas that I was seeing was in this nice blue spiral galaxy. Here's another detection. This is not an AGN either, but it's interesting because all of the H1 in this galaxy was expected to be in one of my AGN galaxies. And this had never been seen before. This galaxy is new. So it's super, super faint. You probably can't even see it. It's right about there. But it has almost 10 to the 8 solar masses, so sun masses of gas, which is crazy for this teensy tiny thing that's super faint and you can't see any stars. But there's a lot of gas there. Here's one of my non-detections. As you can see, there's no signal in the center where my target galaxy should be. It's just noise across the image. And if I plot just all of that together, we see, yes, okay, maybe there's a little bit of something in my galaxy, but there's no significant amount. So I'm not going to mention that. And so the summary of these gas observations is that we have detected none of our target galaxies. None of our low-mass AGN has significant amounts of H1 in, what was it, 6 hours of observations per galaxy? Yeah, we could spend a lot more time, but how far are we willing to go on this? So we've detected several companion galaxies, which is nice. That tells us that our instruments weren't wrong, weren't doing something funky. We've discovered an extremely faint low-mass galaxy. I'm working on a paper in this. And the interesting thing is that we have upper limits on what these H1 masses could be. And we have those set around 10 to the 8 solar masses. And for their stellar masses, which were about 10 to the 9 solar masses, that means that the gas fractions, so the amount of gas divided by the amount of total mass, stellar plus gas mass, the gas fractions are at most 10%, which is low for a low-mass galaxy that you expect to have a lot of gas to form a lot of stars. So these AGN in low-mass galaxies are gas poor. And so I'd like to just wrap up a little bit and say that I've talked about how a galaxy can stop forming stars. You need its reservoir of cold, dense gas to be affected in some way. You need to either remove the gas from the galaxy or you need to heat it in some way. And these mechanisms can be internal or external to the galaxy, but you need to distinguish between where those influences are coming from if you want to do anything with determining individual effects on the galaxy. The quenched low-mass galaxies that have AGN show a preference for isolation, which suggests that the environment was not the main mechanism for quenching these galaxies in the first place. And these low-mass galaxies with AGN have low gas fractions. And I didn't mention this before, but all of those 10 galaxies that I got observations for, they were across a range of environments. So some of them were isolated, some of them had companion galaxies, some of them were in much larger groups. But the point is that across the board, we didn't detect any of them. And so it looks like the environment was, again, not playing a role in quenching these galaxies. And so with that, I will take any questions. Thank you.